All right, team. Today we're going to look at a method, a visual method, graphical method that we can use to evaluate how well our data fit a certain distribution. Distribution, goodness of fit. And we're going to, of course, just to keep it simple, look at how normally distributed are our data. And that's going to be important because most of the tests and eventually the linear regression analysis that we're going to be using assume some level of normality of some aspect of your data. So you can do what we're doing, you can do this with any distribution, but we're going to do the example with a normal distribution. And so what we're going to do is called a quantile-quantile plot. And first I'm going to kind of show you what that looks like, and then we're going to do some definitions. The idea here is that you have your observed values, so X observed, and we're going to have quantiles of those, and then we have X expected if they were normally distributed or if they came from some other distribution that you're testing. And so there's going to be a line and then there's going to be data points. And they might follow along that line really well, or they might diverge from that line. It just depends on your, basically, if you looked at the histogram, that's one way to visualize this. This is another way. So what a QQ plot is, or a quantile-quantile plot, is comparing the quantiles of your data to the quantiles that they would come from if they were from a certain distribution, any distribution, in this case, normal distribution. So what is a quantile? Let's look at that. Oh, we happen to have a nice little figure here. Let's go look at this figure. So I'm going to just zoom out a teensy bit. A quantile represents, it's essentially, it's a special version of a percentile. Okay, so let's start with percentile. Percentile, you all know this, right? It is a value of a random variable. Of a random variable from an ordered, so from small to high, right? Below which X percent of values fall. Okay, so if I have a 90th percentile value, that's the value of X or Z, if we're looking at the Z scores here. But if it's just some data that we're interested in, average daily stream flow at a stream gauge, it could be the load-bearing capacity of soil, right, of a bunch of different samples. If you order them and you calculate the percentage that fall below, then that's a percentile. We can calculate the 10th percentile, the 90th percentile, the 99th percentile, right? So 90th percentile is going to be somewhere over here where we have 90% of the probability below that. So that's percentile. Quantile, these are going to be values with equal probability between them. That's one way of saying, that's kind of a coarse way of saying that. If you look at this, we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've got 16 values. So these are basically 16 Z-scores. And if you were to calculate the area between all of these, that's simply going to be, if there's 16 values, then we're going to have 17. So I think it's going to be 17, 1 divided by 17. So these are all equal areas. So this is 1 over 17, if I'm getting that correctly, 1, 2, 6, 12, 13, 16, 17. Yep. So this is 1 over 17, 1 over 17, 1 over 17, right? And so all we did here is we said we wanted quantiles for 16. We wanted 16 values, calculate the area, and then distribute those along the distribution such that they have equal area. And if you look at the spacing of these z-scores, each of which have an increasing probability of 1.7 of 1 over 17, you can see that they're distributed not uniformly, right? They're not evenly spaced. And that's what gets at this quantile, because to get to 1 over 17, we had to go all the way over here on the tail, but then they start to bunch up the closer you get to the peak, and then they spread out again, right? So that's what makes quantiles kind of interesting. So values along a distribution with a certain percentage of observations or area falling below at equal intervals, right? All right, so let's look at how we can make a QQ plots. And we're actually going to go over to Python to do that. But I forgot I wanted to show you this. So we looked at the PDF, now we have the CDF. So here are those equally spaced values, the Z values, right? If we go up to the CDF curve and come over, you can see that they now have, they're not evenly spaced on the Z axis, but they are evenly spaced on the cumulative probability axis, which makes sense because we said they had equal probability in between them. So we can use the CDF then to calculate the Z-scores, which is also the PPF function in Python. But if you look at this, this is going to be equal cumulative probability, map it onto the cumulative distribution function, and convert it to a Z-score, and then you get that altering or kind of differentially sorted Z-scores. All right, a little bit more about QQ plots. Here is a QQ plot for the normal distribution. In the center, you have a normal distribution. And you can see that the points, the expected observations on the y-axis, the z-scores on the x-axis, you can see that they follow that line pretty perfectly. And then we're looking at different levels of skewness. So here we have a negatively skewed distribution, and it shows kind of a curved QQ plot relative to that straight line, concave downwards. And then here we have a positively skewed distribution. You can see how it diverges from that straight line. So the idea here is that you're seeing more values than you would expect from a normal distribution coming earlier and fewer coming later. And then here you have fewer values than you would expect from the normal distribution coming earlier and then a lot more coming later. So that's how this plot can visually help you determine if your values, if your distribution, if your sample comes from a certain distribution. So again, they're using the normal distribution and it's showing how skewness influences what the QQ plot looks like. The less linear your data are on the QQ plot, the less likely they come from a certain distribution. So let's jump over to Python. And I'm sharing Python code with you all that walks you through this process. All right, so we're going to look at first just a sample from a normal distribution. And that green represents the normal distribution, the green curve, and then the histogram represents that sample. Okay, so it's not, you would look at that sample, if you didn't know it came from a normal distribution, you might not say it's normally distributed. But let's make a QQ plot and see. All right, so step one is what's called the plotting position. And this is a really important formula. It's really basic, but it's really important. And what it does is it allows us to sort our data and calculate the probabilities of those values. So the way this formula works is that we have a sample size of n plus, or of n, and then we're going to calculate the probability of seeing that position in a sorted data set where we sort from high to low, and then we assign it a probability based on a rank. So M is rank, where 1 is associated with the highest value in the sorted data, and then we're just dividing it by n plus 1. So the probability is really basically just rank 1, 2, 3, 4, 5, etc., divided by n plus 1. So this is what that looks like. First, we're going to sort our x values from that sample. And then we're going to calculate the cumulative probability. So it's just this formula, and then we're adding it up for each number. So you can see we have 1 over n plus 1, and we are going to keep adding those values together to get cumulative probability. Okay, so that's going to represent the percentiles of our sample. And then we're going to calculate the theoretical quantiles of those values based on these cumulative probability values. So we just said we had a sample size of, let's see here, where is our little sample there? 25, so that's our sample size. And we are going to sort those data, that random sample. We're going to calculate this rank, right? And so the rank is going to be 1, 2, 3, 4, 5, 6, 7, 8, all the way to 25 divided by 26. We're going to do a cum sum. And so that's what this shows right here. So this is the cumulative sum of these probabilities. And then we're plugging these values into the PPF function, and it's going to spit out z-scores for those values. All right, so now all we're doing then is just plotting those theoretical quantiles, which is just what would the probabilities be, what would the z-scores be for those probabilities, and then we've got our values right here. So if they in fact follow normal distribution, then they should line up on that line. And I'm doing it two ways here. I'm kind of showing you how to do it manually, and then there's a built-in function to do it. So the built-in function to make a QQ plot is called Prob plot. And you can see where we import it right here from SciPy stats. So you import Prob plot, you just give it your sample, you give it the distribution you want to create a QQ plot for, and then the rest is history. This just tells you to plot it as two plots. But if you were just to do these two arguments, you're going to get a Prob plot that looks like this. All right, so we're going to look at this. We're going to say, do we think our data come from this normal distribution? Well, it's not a sure test, right? There are significant tests that you can do. We're not going to cover that in this class, but it gives you a visual tool in addition to the histogram function or the histogram plot to see how normally distributed your data are or how well they fit that distribution. So I'm going to look at this and say, you know what, it's not perfect, but there's a little bit of scatter, but overall it follows out pretty well. All right, to summarize, QQ plots are taking a sample. In this case, we took a sample from the random distribution with a mean standard deviation that were defined. We took a random sample of 25. We sorted those data and ordered them. And then we just said, okay, if we've got 26 values, we're going to create this, what's called a Weibull plotting position formula. And it's just rank divided by n plus 1. And so this is just 1 over n plus 1, plus 2 over n plus 1, plus 3 over n plus 1, et cetera, et cetera, et cetera, all the way up to the top. And so that cumulative sum gives us these cumulative probabilities of seeing those variables. And so if you were to line up the sorted X data with these values, this is basically the probability of seeing those values. And then we calculated the normal quantiles for that, which is just the Z values associated with those cumulative probabilities. Finally, we plotted everything. We plotted the order values. So these are the expected, or sorry, the observed values plotted against the expected values, those theoretical quantiles, if they came from a normal distribution. All right, so that's QQ plots for you. Thanks for tuning in.